Okay, so welcome back. And what we're gonna talk about today is chapter 4, which is about model selection. So what we covered so far, is in a sense, well, mostly about the estimation. So start with motivation. So what we covered so far was about studying the how we can derive the properties about what we really care about using sample-based estimate. In particular, so far, the main things that we talked about was risk of an hypothesis, as well as empirical risk. And many of the results we looked so far was about the relationship between the two. And then these relationships were given in the form of the generalization bound, which say with probability, at least 1 minus delta, for every H in the hypothesis, the risk is going to be bounded by empirical risk, plus some extra term. That extra term is coming from Rademacher complexity, plus some quantity that's coming from the accuracy of these statements together with the sample size. And this is in the proof, this coming from the use of concentration inequality. And we replace this Rademacher complexity to something that we can compute combinatorially. So one option was to replace this Rademacher complexity in terms of growth function, which was m over 2 growth functions m. And then later we replaced this by the VC dimension, which was m2 of em over d. So then I said this, the use of the growth function VC dimension is a more approximate notion of measuring the complexity of our hypothesis class. So in some sense, although that this chapter is titled as a model selection, this chapter is really about how to convert these results to design an algorithm. So design and analyze an learning algorithm. But the kind of things that we're gonna look at is a bit different from what you're gonna see in the algorithm course. In the algorithm course, we look at very many details about this algorithm design. For instance, the choice of data structure, and then particular tricks that optimize certain steps of the algorithm. But the kind of algorithm that we're gonna look at, the kind of algorithm that we're gonna look at in this chapter is what I call idealized algorithm. Which means that, in a sense, these are not really an algorithm. It's just descriptions about some optimization problem. We don't have a way, maybe in some cases, we don't have a way to solve that optimization problem. And because some quantity is, it requires us to optimize over infinitely many entities, or something that appears in the optimization objectives, maybe not very computable. But still, that gives a direction towards designing the real implementable algorithms. So that's the kind of things that we're gonna look at. So idealized learning algorithms are what we're gonna look at, and we will analyze these algorithms, okay? And then in particular, we're gonna use some of the results that we studied before, especially this result, this uniform bound result, which involve Rademacher complexity. That will appear and play an important role in the discussion of this chapter. Okay. So now let's try to answer this question and then see where this model, the idea of model selection actually comes from. So one naive answer to the question that I just raised, how to design and analyze a learning, how to design a learning algorithm, there's actually a very immediate answer. Which is doing so-called empirical risk minimization. What is the idea? The idea is that the empirical risk minimization is given input, which is a sequence of labeled examples, which is going to be input and output y of size m. And then we're gonna assume output it. We consider classification problem. So output is just -1 +1. So we are given something like this. And then we have a hypothesis set H. So what we're gonna return? So in this empirical risk minimization, the output is something that minimizes the empirical risk. So this is called ERM over sample S. What it does is that it's a minimizer, so it's an argmin over our hypothesis set, such that it minimizes empirical risk. And we give a reminder of this empirical risk is defined by 1 over m. It's a Williams error. It's equal to 1 to m, where our hypothesis didn't get the right answer, doesn't get the right answer, we get a penalty. Okay? So this is an average error. So that is, so what we are doing is we find an hypothesis that minimizes the risk. Okay, so this looks like a reasonable choice because what we really care about is the generalization error, which is R of H. This is what we care about. And then this empirical risk, what I put here, is a good proxy of the real risk. So finding some good, minimizing the finding on hypothesis that minimize this empirical risk looks like a reasonable choice. And maybe you might also think that this may be the only way, I mean, to go about this learning problem, only sensible way to go about and solving this learning problem. It turns out we can actually do better in many situations. So how can we do better? Again, this empirical risk minimization is called, I'm gonna write ERM. So we can do better than ERM using the idea of model selection. Which is gonna be the key topic that we're gonna study in this chapter. So what is the idea in a high level? The idea goes like this. So instead of thinking a single, so I'm gonna draw some region. So this region is a set of all the hypotheses. There is one hypothesis for H0, another hypothesis H1, and so on. So empirical risk minimization just said there exists a hypothesis at H, And then we search something that gives the best result in terms of samples. Okay. But in the model selection idea, we impose a structure on the hypothesis set. So instead of thinking just single hypothesis set, we consider hypothesis set, structure the hypothesis set. Typically, the hypothesis structure has some subset relationship. So we have one hypothesis set called H0. And the other hypothesis set is larger, which is containing everything in H0 plus something extra that's called H1. Then the third one is even larger, everything H0 and H1 plus something extra that's called H2 and so on. So we consider, instead of saying that we have a single hypothesis set H, we consider the hypothesis set, we say hypothesis set it consists of, well, can be understood as a union of H of K, natural number. So we, in a sense, made our problem have more structure. And then what we do is that we do two-level search. This doesn't mean the search is happening one after the other. Search can happen simultaneously, but we are searching two things at the same time. But then this two-level search, try to find the appropriate hypothesis at HK. At the same time, it also tried to find a good hypothesis in this HK. In some of the algorithms, which there is something called Endfolds cross-validation. I think you do Endfolds cross-validation in many different applications if you are familiar with machine learning. And also what I'm talking about can also be understood as this hyperparameter search that's often done by this cross-validation and so on. But in the specific setup that I'm going to explain to you, this Endfold cross-validation can be understood as an approach that search both this HK and H at the same time. It can be done simultaneously. No, so not simultaneously, one after the other. So you first find a good hypothesis set, HK, and then you find a hypothesis in that hypothesis set. So that kind of what we call Endfolds cross-validation is going to be an approach to do this. And the other approach, which we will call structural risk minimization, it will search for hypothesis set and good hypothesis at the same time. Yes. That is called what we're gonna study, which is called structural risk minimization. And right, so these are so that's the idea of doing simple model selection, which is instead of saying our hypothesis set is a monolithic, it's just a single set without any structure, we impose a structure. Specifically, we say that it's the union of the larger, smaller hypothesis sets. And then we do two-level search. We search for appropriate hypothesis set. At the same time, we search for appropriate hypothesis in that hypothesis set, sometimes at the same time, sometimes one after the other. If we do so, then often we get a better hypothesis. So we can get a better hypothesis in the sense that we can get R of H, which is better than just searching H in the large set, the single set H. And also this algorithm, the kind of algorithm that can be derived in this approach is sometimes more efficient. And this idea, again, if you are familiar with machine learning, if this idea is not so foreign to somebody who are familiar with machine learning algorithm. That is because whenever people use so-called regularizer, often that boils down to do this type of this two-level search in a simultaneous sense. So they search for hypothesis and hypothesis class at the same time. Okay. So what we're gonna study is that, the key things that we're gonna study in this chapter is to analyze these idealized learning algorithms. So we will study idealized learning algorithms. And in particular, we're gonna study so we will analyze this empirical risk minimization. And then we also study some different learning algorithm that do this model selection. In other words, that impose a structure on the model and do this two-level selection. Okay. So let's start with some basic. Now, before actually talking about an algorithm, there are just some very useful concepts that will help us to design an algorithm, especially in the context of model selection. So this is the textbook. It's called estimation error. And approximation error. Okay. So what are these? So given a learning problem, think about learning. What is a learning problem? Learning problem is we are given a distribution D, the probability distribution on the input and output. So this is, it's called a stochastic scenario that we covered when we discussed this PEG learning part. So this is given, and then we are also given a set of samples. Which is a labeled examples, size M. Then we want to find H that performs well. So ideally, whose R of H is small, as small as possible. Okay, so that's our learning scenario. And we're gonna assume that Y is -1 and +1. So in this learning scenario, this is what we studied already before, but so we can ask what the following question. So suppose we are allowed to choose a hypothesis as we like, okay? So if we do so, what are the minimum achievable errors with minimum achievable generalization? So what is the best? Best function H, it goes from X to Y in terms of risk. So that minimize R of H. And we already learned this. This is, the answer is the base hypothesis, sometimes called base classifier. And then how does it define? We say that if we have an f of x, then it will do case analysis. We compute the, so this is something that we cannot really compute, but this is, if this exists mathematically, we say if the probability of its label becomes conditional, okay, label is equal to 1, given x, is greater than equal to probability of label becomes -1. If that's the case, we return +1, otherwise return -1. It turns out this is the best hypothesis in the sense that it has a minimal generalization error. So for this Bayes hypothesis, the minimum generalization error is called Bayes error. I think sometimes called Bayes. It's Bayes. And that is, in the textbook, it's written as R star. I mean, you can, if you do some computation, that is exactly like this. It's an expectation over where X is a sample from some marginal distribution on X. And then we compute the minimum of conditional probability of y is 1 given X, and conditional probability of y has a -1 given X. So we take the minimum, and it turns out that's the minimum error that we can achieve. Okay. Now let's go back to our algorithm setting. In the algorithm setting, we have a fixed hypothesis that this curly h and small hypothesis small h. So then we can say for given hypothesis, we can define the following concept, which measures how well our hypothesis is doing. I mean, we just noticed that this Bayes error is as good as we can get. So we can define the following quantity, which is called excess error, which is defined of hypothesis H. That is defined to be R of H minus R star. So this means, compared to the best, how worse we are doing. Okay, so that's the idea of this excess error. Find it this way. But then this excess error can be decomposed into two parts. So R of H can be written as infimum over H. This is R of H. Let's put it H prime plus infimum H prime minus R of H prime minus R star. So, it's just simple arithmetic. We just add and subtract the same quantity, which is infimum of something. Okay. But then, if we decompose it, then we can have a decomposition of excess error in terms of two terms. The first term, this one is called estimation error. And this second term is called approximation error. Now, for each hypothesis, then we can say, what we really want to achieve. We want to achieve something, find something, some hypothesis that has as little excess error as possible. Okay, we want to pick a hypothesis, design a hypothesis set. We want to pick a hypothesis set H, where the finding this hypothesis with small excess error is easy. Okay, what is finding a small hypothesis with a small excess error is easy. So that's what we want to do. But what does this mean? So what we want, pick H such that finding small is easy and doable. So what I mean by easy and visible, what I mean is that easy means the from samples, we can't really access this risk directly. So we have to do some find age based on the sample. So based on the sample, we should be able to find some good age. At the same time, feasible, by feasible, I mean that if our hypothesis set just have a one hypothesis age, okay, then finding the small excess error is not going to be possible at all because our hypothesis set is too, it's too crude, it's too simple. So we want that our hypothesis set is complex enough. At the same time, we want that searching over our hypothesis set becomes easy. That's directly related to these two errors that I just described to you. Now, what is the excess error? The excess error is decomposed by the estimation error and the approximation error. So if our hypothesis set is very rich, this approximation error, the second term, is going to be very small. Okay. On the other hand, because our hypothesis set is so large, based on the sample, finding some hypotheses which have a small estimation error may be very difficult. Okay, because if our hypothesis, the kind of lesson that we learned from the generalization bound is that if our hypothesis set is very rich enough, very rich, so then the finding information about risk from sample requires more samples. It requires more examples. Okay, so the reducing this estimation error, if this hypothesis set becomes rich, then it's going to be difficult. So what we have to do in order to this model selection style, the learning algorithm, is that we have to pick a hypothesis, well, not necessarily model selection style learning algorithm, but if you want to have a good learning algorithm, all we have to do is that we have to pick a hypothesis set that give a good balance between this estimation error and the approximation error. It has to be rich enough so that this approximation error is small, but at the same time, it's not too complicated so that it's easier to reduce this estimation error based on sample. Just to sum up, the message here, some of the things that the real contents here is that the remainder of base error, which is the minimum error that we can achieve. Based on this, we can define excess error. And excess error can be decomposed by estimation error and approximation error. And that goes to the opposite directions in terms of complexity of our hypothesis set. Hypothesis set is complex, approximation error is small, but estimation error is going to be large. And the hypothesis set is simple, then opposite situation will happen. So finding the right balance between the two, that's going to be the key of designing a good learning algorithm. So having said this, let's now move to the real analysis of the algorithm, which is the empirical risk minimization. So before talking about algorithm that involves this model selection idea, to start with something very basic, which is risk minimization. So it's called ERM. Okay, so here's as I said, the idea of empirical risk minimization is really simple. So what's the algorithm, or the idealized algorithm, the algorithm takes input. So input is sample, which is a sequence of examples. some e to the m. So as more accurately, it's going to be x1, y1, up to xm. Right? And then what we're gonna do, the output is we're gonna find h, the hypothesis in our hypothesis set based on S. But that's going to be the one that minimizes the empirical risk. Okay. So that's a simple algorithm. And then what we want to do now, okay, we want to analyze this algorithm. Okay. So one thing we want to do is to analyze its estimation error. What was the estimation error? So say something rigorous. About its estimation error. So estimation error is going to be R of H ERM minus increment R of H. Okay. So here's a result that gives the information about this. Say that it says the following. I mean, the textbook is not written as a theorem. It's just made this type of result is just mentioned in the text. So I did it as a theorem. So it said we have a probability bound. So this empirical risk, the result of empirical risk minimization is bounded by, let's just write it as an error form. If this error is bounded by epsilon with this probability, at least this probability. One minus one. So I mean, so this with the result, I mean, if you see this, it's like I mean there are a bunch of numbers, so what does it really tell us? So I think the form that maybe if you looked at the Rademacher complex multiple times, form that a bit more familiar with is the delta form. So this is equivalently we can write this theorem this way. Delta. I mean, there are quantifications that I didn't really explain here. It's not right, the quantification for. If instead of epsilon, if you write it in terms of delta, that's this form. Probability that increment is bounded by 2 Rademacher complexity plus gonna be 1 minus delta. So with high probability, the estimation error is going to be bounded by 2 times Rademacher complexity and 2 times some term that's more, that you perhaps saw. Something looks a bit similar to the term that you saw in the the Rademacher complexity generalization bound. The difference is, in the Rademacher complexity generalization bound that we talked about, it has a no number 2 here, and then there's just it's a 1 over delta, and there's no extra term. But in this case, we have a number 2 appears in the multiple different places. But the form is similar, which means that this result is derived from the generalization bound that we described before. But it's not about the generalization bound. It's really about the performance of the algorithm, which is we have the result of the algorithm and we compare it the best we can achieve, and then we talk about probability bound about it. So now the question becomes, how to prove this? Okay. So the textbook gives a result. Something called proposition 4.1. Then if we use this proposition 4.1, then we can prove this theorem. And proposition 4.1 uses the generalization bound on the Rademacher complexity. Okay. What is the proposition 4.1? First, mark this theorem. You can recognize. So the proposition 4.1 says the following. Ability of ERM solution and infimum bounds is greater than epsilon. So we are thinking about the complement scenario of the statement that's mentioned in the theorem. This is going to be bounded above by the following. Supremum H minus. So the error of the sample-based estimates, the supremum error of the sample-based estimate is greater than epsilon over 2. So that's the proposition that we're gonna prove soon. But here's what I want you to do. So try to use this proposition to prove this theorem. Okay, so I will give you 5 minutes to do so. So let me show you a form that's a bit easier to use. Some form that's a bit easier to prove. It's the opposite case. So it's greater than epsilon, and that is found above negative. The exercise. It's not so easy. Prove theorem. Same proposition 4.1, and this Rademacher complexity found. Okay, so let me show you how to do this. So we first apply the proposition 4.1. So HS, ERM minus infimum. So estimation error is L is to epsilon. That is by proposition 4.1. It's bounded by primum H R of H minus R of H is greater than epsilon over 2. But what does this mean? This means that primum is greater than epsilon over 2, and that we have a strict inequality. That means either, so we have a two case, either there exists a hypothesis such that R of H is greater than S of H. S of H plus or there exists H in H, here R of H is smaller than L of S of H minus epsilon over 2. Nothing special, there's no inequality here. We just rewrote the statements. This is statements. In terms of the, we just removed the supremum there. But then the right-hand side, now we can apply the union bounds. So we have an or here. So that means probability of something or something is bounded above by probability of something plus probability of the other things. So we have probability of there exists H R of H greater than sub H plus epsilon over 2 and probability of H R of H is bounded by above minus 2. Now, how can we go further? Now we can use a generalization bound. So, based on the Rademacher complexity. Okay. So let me let's go back to this generalization. Let's write it here. Okay. So generalization bound based on the Rademacher complexity. That was the form that we are familiar with is always of this form. So negation form is like this. Plus Rademacher complexity of H. So 1 over delta that is bounded by delta. So this is a negated form of the generalization bound. But now if we take we replace this whole thing by epsilon, let's say epsilon over 2, and then we write delta in terms of epsilon, and the form that we get is the following. It's going to be spread here, probability of epsilon over 2. That's going to be bounded by then that's I don't have enough space. Let's create some space. So it's going to be bounded by like this. So we have epsilon over 2 minus Rm of H squared 2n minus exponential. So if we solve this one in terms of delta, that is what we're going to get. So that's the quantity that we're obtaining here. So if we plug in that quantity, So use this form. Then for the for this part, the first part, we can apply this. And that will be bounded by minimization S2M epsilon 2. Yeah. And it turns out something like this also, the dual version of the statement that I wrote here is also true. So we have this inequality and it's bound. But then the dual versions, what this bound is saying, this says that the risk becomes too large compared to the empirical risk. And so the risk R of X becomes too large compared to the empirical risk. So we can now think about the version where risk is too small compared to the empirical risk, which means that we can replace this less. We can replace this greater than in terms of less than, this plus in terms of minus. This means the risk is too small compared to the empirical risk. That's going to also be bounded by exact same probability, and the proof is going to be exactly the same. So by this dual version of the Rademacher complexity generalization bound, the second term will also be bounded by the same probability. Number 2 Rn of each square. So if you add them together, you will get the result claimed in the theorem. Theorem said this is going to be the generalization. The bound on the probability. And now the question becomes, so what we did that we used proposition 4.1 that compares the large probability of large excess error, large estimation error with with some other quantity, and then use it to show the bound the probability of the estimation error being large in the empirical risk minimization. So another question is, how can we prove the proposition 4.1? Here's a proof. Says that bounded by so what appears on the left-hand side of inequality is what we care about. And then what appears on the right-hand side, it is something that we are used to, which is the difference between risk and empirical, the uniform bound on the difference between the risk here and then the empirical risk. Okay. So that's give a stepping stone to let us use the generalization bound for based on Rademacher complexity. Now to prove this proposition. Now this proposition. proof is not so difficult, but it uses some idea. So let's pick. Right. So what we're gonna do? So we will show that the R of HS ERM minus it's going to be bounded by 2 times Riemann over R of H sub H. So we will show this. So then proposition follows, because if this is always true for any S, and we're gonna, if we show this statement that I just shown here, this statement, and that will imply the proposition, because the left-hand side of this inequality is greater than epsilon, then the right-hand side is going to be greater than epsilon as well, from which the proposition will follow. So then the question becomes how we can show this. Okay. So to show this, what we will do, we pick. The tricky part of the proof is there is an infimum here. And doing something directly with the infimum is not so convenient. So we're going to replace infimum by producing some gap. So we pick epsilon 0. So this epsilon 0 has nothing to do with epsilon here. Okay? It's something that we introduced to deal with this infimum. If we pick an infimum, then there always exists AC0. Okay, let's write it as H0, such that H0 is quite close to the infimum in the following sense. The risk of H0 is plus epsilon 0. So that's by the definition of the infimum. Whenever we create some small gap like epsilon 0, we can always find something that's bound by, that is close to the infimum up to epsilon 0. Okay, so that's what coming from the definition of epsilon, the infimum. So then we do the usual trick. Usual trick is, we add and subtract the same thing and then do some manipulation about it. And minus infimum. And we add and subtract this risk of this hypothesis is 0. And then add 0. So if we do so, then we get, because the RH0, and because of this inequality, we can obtain the following inequality. Minus 0 plus epsilon 0. So then next step is, so far we haven't used the fact that this HERM is an optimizer. It achieved the minimum empirical error. So we're gonna use this. So to use this, we introduce the quantifier, doing some similar idea. CRN minus S CRN. Same thing. So H0 plus epsilon 0. Yeah. But because, this is a minimizer, if we replace its argument to H0, then its risk will grow. Its error will grow. Okay, so we use this fact to obtain a new bound. Then by replacing these two guys by the absolute value will only increase the values. Then if we take the supremum over all H, that will bound to each of them. Plus epsilon 0. And this is true for all epsilon 0, so for epsilon 0. So we get this inequality that we wanted to prove in the beginning. So that gives the proof of this. Yeah. Okay. So where we are, and we took an empirical risk minimization, and then we show its general, the bounds on its estimation error, which is, let's use many colors, bound on estimation error, which is given this theorem, but maybe a better way to understand this, the estimation error is the one that's given below. The estimation error is bounded by the quantity that I wrote here with a high probability. And then the key step of the proof is to relate the probability of in this estimation error is large with the probability of the difference between the empirical risk and the risk becomes large. So that's an empirical risk minimization, and we get an analysis about it. It's an estimation error. But now one thing that you can notice in the result is this quantity. So as I said, if you want to have a small approximation error, which is the difference between base risk and the infimum that we have here, so then our H has to be rich, which means that which implies in most cases, this Rademacher complexity will become very large. So then by just looking at these theorems, it confirms our basic intuition, which is that, if we just form a single large hypothesis set and search for a good hypothesis there, then we can reduce the approximation error. But as this theorem indicates, our estimation error will remain quite large. Okay. So what should we do? So that brings us to the what we call structural risk minimization. Okay, so 4. So I will perhaps explain the idea of this idealized algorithm today, and then the analysis will be presented on Thursday. So how this structural risk minimization works. So the key idea is that instead of having one hypothesis set, structure the hypothesis set. As follows. So it's not a single hypothesis set, it's a bunch of hypotheses together. Extra number, and it's okay. Such that this hypothesis set grows. If we So if you increase k, our hypothesis set becomes more and more complex. Okay. And then, so now the real algorithm looks like this. So give input is usual. Implicit input is a distribution. So this is not really an algorithm, but as I said, this is an idealized algorithm. This is a distribution. So probability on x and y. And then I have a sample, which is sampled from this distribution. Then what's going to be the outputs? Output is something called structure SRM. Output is something that minimizes not a risk but something different. So it's a argument K, and then also hypothesis in each of K, such that minimize this quantity called f of K in H. The f of K in H have two things. So it has some expected thing, which is a risk, empirical risk. You have to have a small error with respect to sample. So if you just write it like this, that's exactly the same as empirical risk minimization over the entire age. Okay. So if you say this much, that's exactly the ERM that we talked about before, but it has some extra term. This extra term is Rademacher complexity for H, HK, plus something that measures the complexity of hypothesis K. So the key idea is that it have these two extra terms that, in a sense, measures the complexity of the the complexity of a hypothesis set. What does it do? So just minimizing this empirical risk boils down to trying to reduce. In this structure, trying to find the k that have the smallest approximation error, which means that very likely we're gonna just find some very large k. On the other hand, this extra term, these terms are there to ensure our estimation error remain very small. Okay, so this structural risk minimization have two components together. The one component is about the approximation error, the first component. Second component is about the estimation error. It tries to keep the complexity of the hypothesis at HK to reasonably simple so that our estimation doesn't really go very, very wrong. Okay. Now, so that's the intuitions, but formally where this actually come from? This actually comes from the generalization bound. So it comes from generalization bound, which is the following. So we have uniform generalization bounds sets for K. So we are not talking about one model, hypothesis set, in other words, one model. Instead, we are talking about many models at the same time. And then for all hypothesis and hypothesis HK, its risk of H is bounded by the empirical risk H plus Rademacher complexity of HK. Log K plus some extra term is then. And that holds with high probability. So compared to the usual Rademacher complexity bound, there is this extra guys, and then there is a 2 instead of 1 here. That is because of this another universal quantification of all K here. So if you do, all the universal quantifications in the negated form, that's taken care of by the essentially union bound, and then this extra terms are really coming from this union bound. Okay. But then the algorithm itself have algorithm itself is using not taking this extra term involving delta, it just involves all the other terms, and then say that we optimize this. And because it's an upper bound, and this upper bound put the right try to make the right balance between the complexity of the hypothesis and then expressiveness of the hypothesis. Complexity of the hypothesis set and then its expressiveness, and also balance between the approximation error and the estimation error. So if we do so, what's going to be its guarantee? Okay, so here's the guarantee of this approach. So this will be theorem. So is it really good? So that's the question that we can ask. And of course, whether it really works or not, that's the most important part is the empirical question. But theoretically, we can also see the results. So we said we can put a bound on the structure risk minimization. And that's bounded by infimum H. So this K of H means the minimum hypothesis set, index of minimum hypothesis set that contain H. Okay. Okay. This is greater than 1 minus delta. And then compare this to the ER guarantee for the ERM. The ERM case. So we have something very similar, but there are some slight difference. So if we run ERM over the entire H, okay, so here's what we're gonna get. So this H is over the entire H. So both the ERM and SRM looks very similar. The first part is our, but here's the difference. There are some difference in this term, but minus delta. So yeah, give me 1 minute, then I'll finish. So the key difference is here. Okay, if you look at the Rademacher complexity in both cases, ERM doesn't impose any structure on this hypothesis, big hypothesis set H. SRM, in a sense, stratify this big hypothesis set H into increasingly more complex hypothesis sets, right? So doing this extra bit of work, in terms of the theoretical guarantee, we can have a stronger guarantee because the one involving above is not with respect to the Rademacher complexity of the entire H, but for some subset. And typically K of H is not going to be very, very large. It's going to be reasonably small. So then the Rademacher complexity that we obtain on the above will be much smaller than the Rademacher complexity that we obtain below. So that shows theoretically the benefit of this structural risk minimization. And in fact, some incarnation of this structural risk minimization appears very often in the machine learning algorithm. Okay, sorry about going over time, and then we're gonna continue to discuss about this on Thursday. Okay, so thank you very much.